Okay, so in this video we're going to learn different ways to calculate nLx. So here's our little diagram of the survivorship curve, the L of x curve. I'm going to use the continuous notation, and we know that nLx is the area in yellow, which is the area underneath the L of x curve between ages x and x plus n. So it's going to be the integral of L of y dy from x to x plus n. So we have several ways to calculate it, and our first way is if L of x is relatively straight, relatively linear, and that happens if, for example, n is short over the interval x to x plus n. If n is short, then we can sort of approximate L of x as being relatively straight or relatively linear. And if that's the case, then we can approximate this area in yellow by a rectangle that looks like this rectangle. If it's linear, then we can approximate the yellow area by the area underneath the rectangle. What is the height of that rectangle? Well, this would be roughly x plus n over 2. This height here is going to be whatever L of x. So the height of this rectangle, which we're going to use to approximate the yellow trapezoid, is L of, let's say, L of x plus n over 2, and the base of the rectangle is n years. So that means that nLx, we're going to approximate that by n times L of x plus n over 2. So there's a problem with that, of course. That the problem is that although we sometimes know what Lx and Lx plus n are, this particular approximation requires that we also know what L of x plus n over 2 is. So that's a problem. If we have full information, then we can approximate it like that. Here's a second way, which doesn't use this x plus n over 2, the halfway point between the ages between x and x plus n. We can approximate this L of x plus n over 2 by saying it's roughly halfway in between L of x and L of x plus n. It's going to be the average of L of x and L of x plus n. So we can approximate that by L of x plus L of x plus n over 2. That's the average of L of x and L of x plus n. So if the slope is constant, that is, that deaths occur uniformly over this age interval from x to x plus n, then nLx will equal, so that's the height, so it's going to be n is the base, n years wide, times L of x plus L of x plus n over 2. And that is a pretty classic formula that you often see. So we're interested, of course, in these slopes, whether they're linear, whether they're straight, or they're not. If the slope is shallow, then it means that L of x plus n is close to L of x. So it's almost a rectangle anyway. And that means that the mortality is low. If, on the other hand, L of x plus n is quite a bit lower than L of x, then it means that a lot of people died, and that means that the slope of the L of x is going to be very steep. So we can tell a lot about mortality by looking at the slopes. We're going to come back to that in a little while. Okay, so now we have the second way to do this thing. Let me make a comment. Let's draw another picture. And this is actually, I think this might be, let's call this a 2.5. Maybe we'll just call it the third way. Okay. And here, let's draw that picture again. Here we have L of x, our L of x curve. We have age x here. We have age x plus n there. And so we want to know this area underneath this curve. And let me make a comment, and that is that we can split it up into two pieces. We're going to split this into a rectangle, rectangle A, and we're going to split this up into a triangle, and this triangle is B. Okay? So now here is L of x plus n, here is L of x, and what is this? This is the difference between L of x and L of x plus n. We call that thing n dx, right? And the width here is still n years. So A, this rectangle A, is just going to be n years times, let's say that's equal to, that rectangle A is going to be equal to n times the height Lx plus n, and this triangle B, if it's still linear, what is the formula for the area of a triangle? It's 1/2 base times height. So that is going to be 1/2, and the base is n, and the height is n dx. You can see that's the height. So if we add those two up, then A plus B should equal nLx. And so this is another formula that we often see for this, which is n times Lx plus n plus n over 2 times n dx. Maybe I should have called that 3. That was like 2.5, because it's very closely related. You could see algebraically they're the same thing. Here's a comment, however. For certain age groups, and I'm going to say age groups at the very ends of the ages, so the very, very youngest and the very, very oldest age groups, it turns out that the L of x isn't quite linear. Let me make a, it's not, people don't die uniformly in that group, so rather than x, and actually let's give an example of like age. The very first year of life, it turns out that the L of x curve does not look straight, doesn't look like that. In fact, it looks sort of curved and concave like that. So, I guess maybe I'll put in this is the straight line, but this is the actual shape of nLx between ages 0 and 1. So for young babies, you know that deaths occur much closer to the birth. So the nLx curve for babies and for young kids happens faster. So the straight line turns out to be, if we tried to calculate the nLx using the straight line, we would overestimate it. We'd include this extra area here that we don't want to include. So when the actual mortality is very, very curved, then the straight line way of calculating the nLx will be too high, and we don't want that. So if we do this thing that we did before, which was to calculate a rectangle for this A part, then the B is going to be less than a regular triangle. So rectangle A, this was rectangle, I'm going to call this thing B still. I'm going to call that A still. So in that particular instance, A is okay. We can still estimate that by n times L1. But in this case, B isn't 1/2 of the base times the height. It's a little less than 1/2 of the base times the height. So what we actually do in formal demography is we introduce yet another variable. And this is something that we call nAx. In this particular instance, we're talking about the first year of life. We'll call that 1A0. But in general, it's 1AX. nAx, and nAx is the number of person years lived in the n years after age X by those who died in the interval X to X plus N. Now that's a little complicated, but it turns out that what we're interested in is calculating these number of person years lived. And we know that they didn't make it to age 1. So we're going to try and calculate all of those person years lived. So nAx is going to be the area here of this curved bit. Now, if, as is a reasonable assumption for most ages, if deaths occur relatively uniformly over the ages X to X plus N, and that's most of them, then nAx is usually equal to 1/2. It's almost linear. For intervals where the L of X is very curved, such as from age 0 to 1, then nAx is not equal to n over 2. I'm sorry, this is 1a, so let's make that n over 2. It is not equal to n over 2, and we'll give some specific formulas for nAx later, but the way we use it is that nLx will equal this A part plus the B part. The A part is still going to be n times L x plus n, and the B part now is going to be n AX, I'm sorry, N, that's an A, NAX times NDX. And we can compare that to what we had up here. We had N times LX plus N, and then we had an N over 2 times the deaths. Here we're going to say, in general, we have this formulation, and this is so important. Yes, you're right. I'm going to draw a box around it. And then I'm going to say, for most age groups, NAX is going to equal N over 2. So now we have yet another column to our life table, that is NAX. Let me continue for just another 2 minutes, and then I will, let's draw another picture here. And what we have here is our L of X for ages X, X plus N, X plus 2N, X plus 3N, X plus 4N, and so on. So if these were 5-year age groups, it'd be like age 0, 5, 10, 15, 20. Okay? And what we're interested in, so this is our L of X curve. And if we were to calculate, so this is going to be nLx, this is going to be nLx plus n, this is going to be lnx plus 2n, and this is going to be nLx plus 3n. So if nLx is the area under the L of X from x to x plus n, so what we can do is we can calculate each of those pieces. And let me say nLx equals from x to x plus n of L of y dy. And we can do that for all of these. So if we were to look at infinity Lx, all of the L of x's, we're going to be doing it from age x onward up to the oldest age of L of y dy, and that thing is going to be all of these little areas all the way out to the right. And what is that going to be? This thing is going to be the total person years lived after age X in the cohort. That's just going to be the sum of each of these little boxes. And we give that a symbol, and we call that, it's a total number of person years, we call that T sub X. So that's going to be the total number of person years lived in that cohort, by that cohort, after age X. And now my question is, what is T of X divided by L of X? That's the total number of person years lived it's the total person years lived by the cohort after age X, and L of X is the number of survivors from our initial cohort of our radix. So those are the number of people who reached age X. So the numerator is the total number of person years lived by that cohort of people who reached age X, and the denominator is the number of people age X. So this thing is the average number of years lived after X. For each individual, that's the average number of person years lived after age X, so that's the average number of years lived for each person who reached age X. So that is the expectation of remaining life at age X, and we call that E sub X. So this is, of course, the most common use of the life table is to calculate this expectation of life after age X, and the special case that we always see is E0. That's going to be the expectation of the average number of years lived after age 0. That means the expectation of life at birth. And if you recognize that we're talking about a conditional expectation, conditional on reaching age X, you can see where the word life expectancy comes from. It actually refers to the statistical operation of a expectation. So when we talk about life expectancy, that may not be what you expect in the colloquial sense of the word expect, but it is consistent with what we talk about as the statistical operation of expectation. The expected value. Notice that E sub X is not monotonic. The way we've constructed it, it can go up, it can go down. It turns out that X plus E sub X is the average age of death for those attaining age X, and X plus E sub X is monotonic. So E sub X is not monotonic. X plus E sub X is monotonic. And X plus E sub X is the average age. If E sub X is the average number of years of remaining life for those who reach age X, then X plus E sub X is the average age of death for those at age X. Okay?